Hey everyone, and welcome back. Today we're going to take a deep dive into the world of instrument flying.
That's right. We'll be exploring how pilots navigate when they can't just look out the window. It's a fascinating aspect of aviation.
It is. Our source for this deep dive is the FAA's Instrument Flying Handbook, and by the end you'll have a solid foundation for understanding how it all works.
It's like gaining a whole new perspective on flying.
Literally. So let's jump right in. Why would any pilot want to go through all the training and effort to get an instrument rating?
Well, imagine you're flying over the mountains and enjoying the view when suddenly you're swallowed by fog.
Oh, wow. Yeah, that would be scary.
That's when an instrument rating becomes more than just a piece of paper.
Right.
It's about having the skill and the confidence to navigate safely when you can't see where you're going.
Okay, so safety is a big reason.
Definitely.
But isn't it also about freedom?
Absolutely. Think about all those times bad weather has kept you grounded.
Yeah, too many.
With an instrument rating, those days become opportunities to fly.
That's a great point. It really does open up a lot more possibilities.
You're not at the mercy of the elements anymore.
I like that.
Yeah.
But the handbook also talks about a mental shift that comes with instrument flying.
Yeah, it's a different way of thinking.
How so?
When you're flying visually, you're relying on your senses and your intuition.
Right.
With instrument flying, you have to trust the instruments,
Yeah.
even when they might seem to contradict what your body's telling you.
That's interesting. It's almost like having to learn to fly all over again.
It is. You're essentially developing new instincts, ones that are based on data and precision.
Okay, so instrument flying is awesome, but let's talk about airspace for a minute.
Okay.
I remember the first time I looked at a sectional chart.
Uh-huh.
It was like a rainbow explosion of letters and lines.
A lot of people feel that way the first time they see one, but there's a method to the madness.
I hope so.
Think of airspace as a way of organizing the skies, like traffic lanes on a highway. And those letters and lines are like the signs that help you navigate those lanes.
Okay, that makes sense. So break it down for us. What are the key things to remember about the different airspace classifications?
Well, let's start with Class A. Think of it as the express lane in the sky. It's generally above 18,000 feet, and everyone up there is flying under instrument flight rules with an instrument rating and talking to air traffic control.
So it's all about efficiency and high-speed travel up there.
Right.
Makes sense. So if you want to cruise with the big jets, you got to be in Class A. What about Class B? Those zones always look like giant upside-down wedding cakes on the maps.
Yeah. Class B is designed to handle the busiest airports like LAX or JFK. It goes from the surface up to 10,000 feet and has those layers that resemble a wedding cake, like you said.
Yeah.
The most important thing to remember about Class B is you absolutely need permission from air traffic control to enter.
Okay.
And once you're in, you'll get what's called separation services, meaning they're keeping you a safe distance from other aircraft.
So it's like the VIP lounge of a busy airport. You need a special invitation to get in, but once you're there, you get the royal treatment. Okay, so what about Class C?
Class C is kind of a step down in terms of complexity. It surrounds airports with control towers, radar approach control, and a certain amount of instrument traffic. You still need to talk to air traffic control before you enter.
Okay.
But the procedures aren't quite as strict as Class B. Think of it as the business class section of the sky.
Got it. So what about Class D? Is that like the economy section then?
You could say that. Class D is your typical controlled airspace around smaller airports with control towers.
Lovely.
You need to talk to them before you enter, but the requirements are generally less stringent.
All right, so we've got the premium classes A, B, and C,
Right.
and then the more relaxed Class D. What about Class E? Where does that fit in?
Class E is kind of a catch-all for controlled airspace that isn't A, B, C, or D. It can start at the surface or at a designated altitude, and it often includes federal airways and transition areas.
So it's the airspace that connects everything else.
Exactly. And then we have Class G.
Ah, Class G. That's the Wild West right now.
Precisely. Class G is essentially uncontrolled airspace.
Okay.
It's where you'll typically find visual flight rules operations, but there are still rules to follow, especially when it comes to visibility and cloud clearances.
So even in the Wild West, there are still some rules to keep things safe. It's amazing how this system, with all its complexities, creates order out of what could be chaos.
It really is. It's like a giant invisible web ensuring that aircraft can move safely and efficiently from small planes to jumbo jets.
But speaking of navigating, let's zoom out a bit and talk about those en route charts for a minute.
Okay.
Those things with their Victor Airways and jet routes look like a roadmap from another planet.
Yeah, they can be a little intimidating at first. It's like a secret code that pilots need to decipher.
Exactly.
But once you understand the language, it's actually quite logical.
So let's break the code then. What are some of the key features that stand out to you on those charts?
Well, for starters, you have the airways themselves. Victor airways are the ones you'll typically see on low-altitude charts.
Mm.
And they crisscross the country, connecting different navigation aids and providing pilots with defined routes to follow.
All right, and what about those jet routes we always hear about?
Those are the high-altitude highways operating above 18,000 feet. They're designed for high-speed jet traffic.
Makes sense. So we have all these airways, but how do pilots actually know what altitude to fly at and that they're clear of obstacles?
Well, that's where those acronyms like MEA, MOCA, and MRA come in.
Oh boy, here we go.
Imagine you're cruising along an airway and you suddenly lose your navigation signal.
Uh-oh, not good.
The MEA, or minimum en route altitude, tells you the lowest you can safely fly to ensure you're clear of any mountains in the clouds.
Oh, okay, so it's like the minimum safe altitude for that particular route.
Yeah, and it also guarantees you'll have a strong enough signal from your navigation equipment.
Gotcha. What about those MOCAs?
The MOCA, or minimum obstruction clearance altitude, is similar to the MEA in terms of obstacle clearance, but it only guarantees signal reception within 22 nautical miles of the closest navigation aid.
Okay. And MRA, what's that stand for?
MRA stands for minimum reception altitude, and it indicates the lowest altitude at which you can reliably determine your position from an off-course navigation aid.
It's incredible how this system, with all its complexities, ensures safety in the skies even when you can't see anything. But let's move on to a specific type of chart I find particularly interesting, the approach chart.
Right.
Those things can look like hieroglyphics at first glance.
Yeah, they can be a little overwhelming the first time you see one. They're like the final puzzle piece, guiding you down to the runway safely in low visibility.
Okay, so imagine you're approaching an airport in thick fog. The approach chart becomes your lifeline. Walk us through how it works.
Think of it as a multi-layered map, with each layer providing specific information to guide you to the runway. It starts with the margin identification section, which tells you the airport's location and the specific approach you're looking at.
Okay, so that sets the stage. What comes next?
Then you have the pilot briefing section, which is kind of like your pre-flight checklist for the approach. It tells you which navigation aids you'll be using, their frequencies, the final approach course, and any special notes or instructions.
So it's all the need-to-know information before you even start the approach.
Yeah.
What are the third section?
That's the plan view, which is basically a bird's-eye view of the approach path. It shows you the routes, the fixes, and procedures you'll need to follow to get from the en route structure down to the final approach course.
So it's like a roadmap guiding you through the airspace around the airport. What about that fourth section?
That's the profile view. It's like a side view of the approach, showing you the altitudes, the distances, and fixes you'll encounter as you descend. It helps you visualize the approach.
Okay, so we've got the overview and the side view. What about the fifth section?
That's the landing minimum section. It tells you the lowest altitude and visibility requirements for landing on this specific approach.
Okay.
It's like a safety net. It makes sure you have enough visual references and are high enough to clear any obstacles.
Got it. And what determines those minimums?
Well, they're categorized based on aircraft approach categories, and those take into account an aircraft's stalling speed. Aircraft with different stalling speeds will handle differently on approach, especially in low visibility.
Okay.
So these categories help ensure each aircraft type has appropriate safety margins. You'll see them labeled as A, B, C, D, and E on the chart.
So an aircraft with a lower stalling speed, like a small general aviation aircraft, might have lower minimums than a larger, heavier aircraft with a higher stalling speed.
Exactly. And you'll notice the landing minimum section will list the minimums for both straight-in landings and circling approaches. Circling approaches involve circling the airport to line up with the runway, and they typically have higher minimums than straight-in approaches.
Right, because circling involves more maneuvering and potentially greater risks, especially in low visibility.
Precisely. And another important thing to remember about landing minimums is that the visibility figures can be given in either statute miles or runway visual range,
Okay.
which is measured by instruments along the runway. So it's crucial to know which type of visibility is being reported.
So it's like having two different yardsticks for measuring visibility.
You could say that. And finally, we have the sixth and final section, the airport diagram.
Okay, what does that tell us?
The airport diagram is like a mini map of the airport itself. It shows you the runway configurations, taxiway locations, and the position of important features like the control tower. It's especially helpful if you're landing at an unfamiliar airport.
So it helps you get oriented once you're on the ground. It's amazing how much information is packed into those approach charts.
It is. It's like a step-by-step guide for landing safely, even in the most challenging conditions.
It really is. But it's not just about charts and procedures. Technology plays a huge role as well.
Absolutely.
Remember when GPS first became available for aviation? It was a game changer.
Yeah.
And the handbook even mentions more exciting advancements like moving maps and electronic flight bags.
Yeah, those have really revolutionized the way pilots navigate. With Moving Map, you're no longer just staring at needles on a gauge.
Right.
You're seeing a real-time picture of your position, the terrain, and even the weather. It's like having X-ray vision for the sky.
What about electronic flight bags? What makes those so special?
Think back to those bulky paper charts and manuals that used to fill up the cockpit. Electronic flight bags, or EFBs, have replaced all of that.
Oh, wow.
They're like digital libraries for pilots containing everything from approach charts and en route charts to aircraft manuals and even weather information.
It's like having a co-pilot who's a walking encyclopedia of aviation data.
Exactly. And the great thing about them is that they can be updated easily, so pilots always have the most current information.
It's incredible how technology is making flying safer and more efficient. But before we get too carried away with the future of aviation, let's take a moment to recap what we've learned so far. We've explored the reasons why pilots choose to get instrument ratings.
Yeah.
We've decoded the mysteries of airspace classifications.
Uh-huh.
And we've delved into the world of en route charts and approach charts.
We sure have.
And we've even touched on some of the amazing technology that's transforming the cockpit.
Mm-hmm.
But our journey into the world of instrument flying isn't over yet.
That's right.
In the next part, we'll be exploring the unsung hero of safe and efficient air travel, the air traffic control system.
Exactly.
We'll delve into how pilots communicate with ATC, the different types of facilities involved, and how ATC helps pilots navigate the skies and avoid hazardous weather. So stay tuned, folks. We'll be right back. Welcome back, everyone. Today, we're going to dive into the world of air traffic control.
It's an amazing system.
It is a behind-the-scenes network that keeps the skies safe and organized.
Yeah, it's more collaborative than people might think.
Oh,
It's a constant conversation between pilots and controllers.
working together to ensure smooth and safe operation.
Exactly.
So let's talk about that communication. What tools are pilots using to talk to ATC?
Well, the most obvious is the radio,
Right.
but it's not just one type of radio.
Okay.
There are NEFOM radios,
Neighbor.
which are used for both navigation and communication.
Ah,
They allow pilots to talk to ATC and receive signals from navigation aids like VORs.
so they're like multitasking radios. What else is there?
Then you have transponders,
Transquaders.
which are kind of like electronic license plates
Yeah.
for aircraft.
Okay.
They transmit a coded signal
Oh.
that ATC can pick up on their radar screens. It helps them identify and track each aircraft.
Oh, so that's how they know who's who up there. Do all transponders work the same way?
Most transponders also have what's called Mode C capability, which transmits altitude information as well.
Interesting.
This gives ATC a three-dimensional view of the traffic. Makes it much easier to maintain separation between aircraft.
That's incredible. It's like they have a live 3D map of everything happening up there. Let's talk about those communication procedures for a sec.
Ooh.
I imagine there's a specific protocol for talking to ATC. It's not like you can just pick up the mic and say, hey, how's it going?
You're exactly right. There's a very specific language of aviation communication,
Okay.
designed to be clear, concise, and unambiguous.
Makes sense.
The FAA Handbook actually outlines the proper phraseology and procedures so everyone knows what to expect and how to respond. It's
Yeah.
all about safety through clear communication.
So it's like learning a new language, but instead of ordering a coffee, you're requesting clearance to land.
Exactly.
Right. So we have the radios, the transponders, and the communication procedures.
Yeah.
But who are pilots actually talking to on the other end? What are the different types of facilities in the ATC system?
Well, let's start with flight service stations, or FSSs. Think of them as the information hubs for pilots. They provide weather briefings, flight planning assistance, and can even help pilots in emergency situations.
They're like the all-knowing aviation gurus. What about when you're actually at the airport getting ready to take off or land? Who are you talking to then?
At the airport, you'll be talking to the control tower.
Okay.
They handle all the traffic on the ground and in the immediate vicinity of the airport,
Right.
giving clearances for takeoff and landing and making sure everything runs smoothly.
I've always wondered how they manage to keep everything running so smoothly, especially those busy airports.
It's definitely a challenging job. It takes intense focus and great communication skills.
No kidding. Okay, so we've got the FSS for pre-flight information, and the control tower for operations at the airport. What about once you're airborne and away from the airport? Who takes over then?
That's when you'll typically be talking to Terminal Radar Approach Control, or TRACON.
TRACON.
They handle traffic in a larger area around the airport, including departures, arrivals, and transitions between different airspace classes.
So they're like the traffic cops for the airspace around the airport.
That's a good way to put it. They're monitoring everything on radar, keeping planes separated, and guiding them safely through their transitions.
Okay. And then for those longer flights, you're handed off to the RTCC, right?
Exactly. RTCC stands for Air Route Traffic Control Center, and they handle en route traffic over large geographical areas. They're the ones who keep those planes flowing smoothly across the country.
It's amazing to think about the coordination involved in keeping all those planes separated and on track. But ATC does more than just direct traffic.
Right.
They also play a crucial role in weather avoidance.
Absolutely.
How so?
ATC uses radar and pilot reports to help pilots avoid hazardous weather. They can advise you to avoid a certain area or suggest specific altitude changes to get above or below a layer of clouds.
Okay.
They can even vector you around a thunderstorm using radar.
So it's a real partnership between pilots and controllers working together to stay safe.
Yeah, you could say that.
Speaking of technology, the handbook mentions something called a precision runway monitor. What is that and how does it help?
A precision runway monitor, or PRM, is a specialized radar system. It provides very accurate surveillance of aircraft on final approach. It allows controllers to monitor aircraft positions with much greater precision, even in low visibility conditions.
Oh, wow.
It can even detect potentially dangerous deviations from the glide path, giving controllers time to warn the pilot and prevent an accident.
So it's like an extra set of eyes for the controllers. Helps them ensure safe landings.
Yeah.
Especially when visibility is limited.
Exactly. And PRM is particularly valuable at airports with parallel runways, where it helps maintain the required separation between aircraft landing simultaneously. But the ATC system isn't just about technology. It's also about procedures and coordination. The handbook mentions something called control sequence.
Control sequence.
Yeah, it refers to the order in which aircraft are handled by different ATC facilities. It's like a carefully choreographed dance, ensuring that aircraft are seamlessly transferred from one controller to the next as they progress through their flight.
So it's about making sure there are no gaps or overlaps in communication as an aircraft moves from one area of responsibility to another.
Precisely. And the handbook also mentions letters of agreement, or LOAs, which are formal agreements between different ATC facilities outlining how they'll coordinate and handle traffic in specific areas.
So it's all about teamwork and communication. It's like a well-oiled machine with everyone working together.
It really is. The ATC system is complex and dynamic, but it's thanks to the dedication and expertise of the controllers and their collaboration with pilots that we can enjoy safe and efficient air travel.
Well, it's definitely given me a whole new appreciation for what goes on behind the scenes to keep those planes moving safely. But even with all that expertise and technology, there are times when you just can't avoid bad weather.
That's right, and that's why it's so important for instrument pilots to understand how weather affects their aircraft and how to handle those challenges. But it's not just about understanding the weather itself.
Okay.
It's also about understanding ourselves. We're not robots.
True.
We're human, and we're susceptible to things like fatigue, stress, and even illusions.
Right.
All of which can have a big impact on our decision-making and performance, especially when flying in challenging conditions.
Okay, so let's talk about those human factors.
Yeah.
How do they come into play during instrument flying?
Well, for starters, instrument flying is mentally demanding. You're constantly processing information, making decisions, and monitoring instruments. Fatigue can set in, reducing your alertness and reaction time.
Yeah, I can imagine that.
And stress can amplify those effects, especially when you're dealing with unexpected situations or challenging weather.
It's like the pressure is building, and it can be hard to stay calm and focused.
Right. And then there are the illusions, which can be particularly dangerous. Our brains rely on sensory input from our eyes and inner ears to help us orient ourselves. But when we're flying in instrument conditions, those sensory cues can be misleading, leading to spatial disorientation.
It's like your brain is playing tricks on you.
It can feel that way. The handbook describes various types of illusions that pilots can experience.
Okay.
For example, one of the most common is called the leans.
The leans.
It happens when you've been in a turn for a while, and your inner ear, which helps with balance, gets used to the sensation. When you level the wings, your body might still feel like it's leaning, causing you to make an incorrect control input.
Oh, wow. So you could actually feel like you're leaning even though the plane is level.
Yeah,
Are there other common illusions pilots need to be aware of?
absolutely. There's the Coriolis illusion, which can happen when you're in a turn and then move your head quickly,
Okay.
like to look at an instrument. The combination of the turn and the head movement can create a sensation of tumbling, which can be incredibly disorienting.
Oh, yeah, like that feeling you get when you spin around too many times and suddenly stop. No wonder it's so important to trust those instruments.
Exactly. And then there's the graveyard spiral. That can occur when a pilot enters a gradual, unnoticed turn. As the turn continues, the pilot might feel like they're flying straight and level, even though they're slowly descending. If they don't recognize the situation and correct it, the spiral can continue and lead to a very dangerous situation.
Those illusions sound terrifying. It's like being tricked by your own senses.
They can be very dangerous. That's why instrument pilots are trained to recognize and overcome these illusions by relying on their instruments. But it's not just illusions that can happen in the clouds.
Right.
Visual illusions can happen too, especially during approach and landing.
Oh, right. I remember reading about those in the handbook, like the runway with illusion. What was that one again?
Well, if you're approaching a wider than usual runway, it might appear that you're lower than you actually are,
Okay.
causing you to flare too high.
So instead of a smooth touchdown, you end up floating down the runway. What about narrower runways?
On a narrower runway, it might feel like you're higher than you actually are, which could lead you to flare too low.
Interesting. It's incredible how our perception can be so easily fooled, even in something as seemingly straightforward as landing an airplane.
It really highlights the importance of trusting your instruments and cross-checking them regularly, especially in low visibility conditions.
So instrument flying isn't just about mastering the technical skills. It's about understanding and managing the human factors
Right.
that can influence our performance.
Exactly. It's about being aware of our limitations, knowing how to mitigate risks, and developing strategies for maintaining situational awareness and making sound decisions even under pressure.
That's a great takeaway. But before we move on, I want to circle back to something you mentioned earlier about how weather affects aircraft performance. Can you elaborate on that a bit more?
Sure, when you're flying in visual conditions, you can see how the wind is affecting your aircraft and how turbulence is bumping you around. But in instrument conditions, you have to rely on your instruments and your understanding of aerodynamic principles to maintain control.
Okay, so let's revisit those basic aerodynamic forces we all learned in flight school. Lift, drag, thrust, and weight. How do those come into play during instrument flying?
Well, when you're flying in clouds or fog, you can't see the horizon, which means you need to rely on your instruments to maintain a level attitude.
Okay,
If you don't understand the relationship between lift, weight, and angle of attack, you could inadvertently stall the aircraft.
stalling the aircraft in instrument conditions sounds pretty scary.
It can be. That's why it's so important to understand stall characteristics and how to recover from a stall.
What about turns? Are those more complicated in instrument conditions as well?
They definitely require more precision and attention to detail. In a turn, you're essentially tilting the lift vector, which means you need to increase the angle of attack and/or the airspeed to maintain altitude. You also need to use the rudder to coordinate the turn and prevent a slip or skid.
So it's a lot more than just turning the yoke or stick.
Right.
It's about understanding how the forces are changing and making precise inputs to maintain a stable turn.
That's right. And the handbook goes into detail about different types of turns, like standard rate turns and turns to predetermined headings, which all require a solid understanding of those aerodynamic principles. And then there's the issue of icing.
Icing. Why is that such a big deal for instrument pilots?
Well, icing can have a dramatic impact on aircraft performance.
Okay.
When ice forms on the wings and tail surfaces, it disrupts the smooth airflow, reducing lift and increasing drag. This can make it difficult to maintain altitude and control.
So it's like the ice is making the wings less efficient, almost like putting sandpaper on them.
That's a good analogy. Icing can also affect other critical systems like the pitot-static system, which we talked about earlier.
Right.
The one that provides information to the altimeter and airspeed indicator.
So icing can lead to inaccurate instrument readings, making it even harder to fly safely in instrument conditions.
Precisely. And in extreme cases, icing can even lead to a loss of control. That's why it's so important for instrument pilots to understand the different types of icing, the conditions that favor icing, and the procedures for dealing with icing encounters.
It sounds like icing is a serious threat, that instrument pilots need to be prepared for.
It is, but with the proper training and awareness, it's a manageable risk.
This has been a really insightful look into those aerodynamic factors that can influence instrument flying. It's clear that a thorough understanding of these principles is crucial for safe operations.
I agree. And in the next part of our deep dive, we'll explore the heart and soul of instrument flying, the flight instruments themselves.
That's right. We'll unlock the secrets of the instruments that guide pilots through the clouds, from the airspeed indicator to the altimeter and beyond.
It's going to be fun.
So stay tuned, folks, as we continue our exploration into the world of instrument flying. Welcome back to our deep dives into instrument flying. We've come a long way.
We have.
We've explored why pilots want to get instrument ratings and how they navigate the airspace. But in this final part, I want to zero in on the instruments themselves.
Yeah, those become your eyes in the clouds, providing all the info you need to maintain control, navigate, and fly safely.
I've always been fascinated by those dials and gauges. They almost seem magical, giving you a sense of what the aircraft is doing even when you can't see anything outside.
It's a combo of clever engineering and some fundamental physics principles. Let's start with a pitot-static system, which is the foundation for several key instruments.
Okay, the pitot-static system. That name sounds kind of intimidating. What is that all about?
It's actually a pretty elegant system. Imagine you're holding your hand out the window of a moving car. Okay.
You feel the force of the air pushing against your hand.
Yeah.
That's essentially what the pitot tube measures.
So that little probe sticking out from the front of the aircraft?
Exactly. It captures the ram air pressure, which is directly related to the aircraft's speed. The faster you go, the higher the pressure.
Okay, so that explains airspeed. But what about the static part of the pitot-static system?
That's where the static ports come in. They're small openings, usually on the side of the fuselage, that measure the ambient air pressure.
Ambient air pressure.
The pressure of the still air surrounding the aircraft, not the air rushing directly at it.
So we have these two types of pressure.
Right.
Ram air pressure from the pitot tube and static air pressure from the static ports. How do those pressures translate into useful information for the pilot?
Think of it this way. The airspeed indicator compares the ram air pressure to the static air pressure.
Okay.
The bigger the difference between the two, the faster the plane is moving. So the airspeed indicator is basically measuring a pressure differential. That's pretty clever. What about the altimeter? How does that use the pitot-static system?
The altimeter actually only uses the static air pressure. As you climb higher, the static air pressure decreases. The altimeter is calibrated to convert that change in pressure into an altitude reading.
It's amazing how something as simple as air pressure can tell you both airspeed and altitude. But the handbook also talks about potential problems with the pitot-static system, like blockages.
Yeah.
What happens if something gets stuck in one of those tubes or ports?
Blockages can lead to inaccurate readings, which is obviously a big problem when you're relying on those instruments to fly safely. Imagine you're cruising along and your pitot tube gets clogged with ice.
Okay.
The airspeed indicator might drop to 0 even though you're still moving through the air.
That would be incredibly disorienting. What about a blocked static port? What kind of problems would that cause?
A blocked static port would affect both the airspeed indicator and the altimeter.
Oh, what?
The altimeter might freeze at a certain altitude, and the airspeed indicator could give you false readings. It just depends if you're climbing, descending, or in level flight. It's definitely not a situation you want to be in.
So it's super important to make sure that pitot-static system is clear and working properly.
Absolutely. Regular maintenance and those pre-flight checks are crucial. But let's move on from air pressure and talk about gyroscopes.
Gyroscopes, I remember those from science class. Those spinning wheels that seem to defy gravity. How are those used in flight instruments?
Think of a gyroscope as a spinning wheel mounted in a way that allows it to maintain its orientation in space, regardless of how the aircraft moves.
Okay.
That's called rigidity in space.
So the gyroscope wants to stay pointing in the same direction even if the aircraft tilts or turns.
Exactly. That's how it's used in the attitude indicator. The gyroscope is mounted so that it remains vertical, like a mini version of Earth's axis. As the aircraft pitches or rolls, the instrument case moves around the gyroscope, showing the pilot the plane's orientation relative to the horizon.
So the attitude indicator gives you that artificial horizon when you can't see the real one? What about the heading indicator? Does that use the gyroscope too?
It does. In the heading indicator, the gyroscope is mounted horizontally. As the aircraft turns, the compass card rotates around the gyroscope, indicating the aircraft's heading.
Wow. It's amazing how those spinning wheels can provide such crucial information. But the handbook mentions that these Gyroscopic instruments need a power source.
Right.
What happens if they lose power?
Gyroscopic instruments can be powered either pneumatically using a vacuum pump or electrically using the aircraft's electrical system. If the power source fails, the gyroscopes will start to spin down and the instruments will become unreliable.
Oh, that sounds like trouble. So it's important to have backup systems.
Absolutely. And in modern aircraft, we're seeing more and more electronic flight instrument systems, which use solid-state sensors and computers to provide attitude and heading information. These are typically more reliable and more accurate.
So technology is constantly improving the instruments.
Definitely. And with glass cockpits and integrated flight displays, pilots have access to even more information than ever before.
It's incredible how far we've come. We've gone from relying on basic gyroscopes and air pressure gauges to having sophisticated integrated systems.
It really is a testament to how aviation technology is constantly evolving, always pushing the boundaries of safety and capability.
Well, this has been an amazing journey. We've explored so much,
We have.
from airspace classifications to the instruments themselves.
Yeah,
Hopefully our listeners have a much better understanding of how instrument flying works.
I hope so too. It really is a fascinating part of aviation.
And I hope it encourages our listeners to maybe even consider taking a discovery flight with an instructor
That would be great.
to experience it all firsthand.
Definitely.
That's all for today. Thanks for joining us, and we'll see you next time.